In the last video, we started to work out a cost function or optimization objective for logistic regression. In this video, we'll derive a simplified version of that and develop our final optimization objective for logistic regression, and we'll also talk about some of its properties. Earlier, we said that we wanted to find the cost function j of theta for logistic regression, and we wrote down the cost function as a sum of costs over the training examples, where we said that the cost of predicting h of x given a label y was this formula that we worked out on the right. The first thing I want to do is take this equation, take this cost function, and write it in a more compact notation. As I do so, I want to notice that in the training set, we will always have y equals 0 or 1 always. In fact, this is part of the problem definition, and so you can safely assume that y is always equal to 0 or 1, and we don't have to worry about, well, what if y were some other value, because in the training set, y is given to us, and a piece of email is always either labeled as 0 or 1, and so y is 0 or 1 always. What I'd like to do is write the cost function as follows. I'm going to write cost of this is equal to minus y log h of x minus 1 minus y times log 1 minus h of x. And I claim that this single equation down here is a more compact, or sort of a summarization of this more complex equation up here with two cases, where in the previous video we said that the cost is this if y equals 1, the cost is that if y equals 0. And this equation summarizes those two cases more compactly. Just to see why that is the case, the two cases we need to concern ourselves with are if y equals 1 and y equals 0. So if y equals 1, then if you look at what the cost function is, the cost becomes, well, this first term becomes minus log h of x. And the second term, well, if y is equal to 1, this term is going to be equal to 0, right? Because if y equals 1, that's 1 minus 1. So if y equals 1, the cost is minus log h of x, which is exactly what we had up here if y equals 1. And very quickly, if y is equal to 0, then in the same way, the cost ends up being minus log 1 minus h of x. And the way to see that is if the cost is 0, then this y here equals 0, so this first term goes away, and then this becomes minus 1 times log of that. And so the cost becomes exactly what we had up here as well for if y is equal to 0. Okay, so this equation over here, this gives us a more compact way to write down our cost function. And in particular, let's write it down in one line. This therefore gives us our final cost function for logistic regression. The cost is our final optimization objective for logistic regression, with the sum of our training set of the cost of predicting h of x on an example y, where, and if you plug in the definition of the cost function that we had previously, it becomes minus 1 over m sum of my training examples of that formula that we worked out just now. And this is nice because it lets us write the entire cost function more compactly on just one line. This is a log. Sorry about the bad handwriting. Like so. And just put big square brackets around that. Okay. So to find the parameters, or to fit the parameters theta, what we're going to do is take our cost function j of theta and minimize j of theta as a function of theta, and this will get the parameters theta that we want. Having learned these parameters theta, if we get a new example on a new input x, say, we would then output h of x, which is of course 1 over 1 plus e to the minus theta transpose x. And that's the logistic regression algorithm in outline. And it turns out that, let's see, so earlier we talked about, maybe we could have tried to use a squared error cost function for logistic regression. And we said that one of the problems with that is that you end up with this highly non-convex function that is difficult to maximize. It turns out that with our current cost function, the one on the previous slide, it turns out that the cost function is convex, right? That function sum from I equals 1 to m of minus 1 over m yi log and so on, right? So that cost function turns out to be convex, and if you were to plot j of theta as a function of theta, you find that it has no local optima. And so if you were to, say, use an algorithm like gradient descent to minimize it, gradient descent should converge to the global optimum. Finally, as a quick aside, maybe a side discussion, on the previous video, I said that we wanted a cost function, if y equals 1, I said I wanted a cost function that looks like this, right? If this is h of x, and this is, let's see, if this is 1, this is 0. So I wanted a cost function that goes to infinity as h of x goes to 0. And similarly, if there was the other case, I guess, if y equals 0, right, I wanted a cost function that goes to infinity as h goes to 1. And it turns out that, well, there are actually lots of functions that look like this, right? There are plenty of functions that blow up and go to infinity at 0, or blow up and go to infinity at 1. And so why is it that we decided to choose the log function? Why did we choose log of x and minus log, I guess, 1 minus h of x? So why the log function specifically? I'm not going to go into the derivation. I'm not going to go into details here, but it turns out that if you look in statistics, there's an idea called maximum likelihood estimation. Sometimes also abbreviated MLE. And it turns out that if you take the idea of maximum likelihood estimation and you apply it to the logistic regression model, then you end up with exactly the cost function that we came up with in this and the previous video. I'm not going to talk about the idea of maximum likelihood estimation, but I sort of just want to say that out of all the cost functions we could have chosen, that there's sort of a more formal mathematical or more formal statistical justification behind it. And of course, the fact that the cost function we figured out is convex and free of local optima, that's another nice bonus.